Good morning. Hello, and welcome to the first asynchronous video lecture of this course, MUSC110, Introduction to Audio Technology. So this is our first asynchronous lecture. I hope that you all had a wonderful and relaxing long Labor Day weekend. I know I did. I actually got a little time to really focus on doing some composing, so I had a great time, and I hope that you guys did too. We're going to get started here this week with this lecture, and we're starting with sound and hearing is what I'm calling this lecture. And to be more specific, we'll be talking about understanding sound from the perspective of physics. In other words, we're going to be looking at some math. Don't freak out once I get to the math part. You aren't going to be tested on any of the math. The reason that I include it is because I think that it's helpful to understand these math, the physics and math side of things, because once we start looking at some of these audio programs and start trying to understand what is actually happening in the computer, a lot of it is just applying these concepts in physics, a physics understanding of sound to these technologies. So don't worry, you're never going to be quizzed on any of the math or anything that's included in this lecture. And if there's some mathematical concepts that today you're just like, I totally did not get that, that's fine, because we're going to talk about them later. And again, like I said, the purpose of them is to help you have a more deep and general understanding of what exactly is happening within the computer or any other audio technology. So we're going to be looking at physics, we're going to be looking at graphs, we're going to be looking at sound waves and some equations. Hopefully I will present them in a way that isn't totally intimidating. We'll also be looking at hearing. In other words, we're going to look at the physiology of the ear, look at the eardrum, look at the ear canal, and understand how our ears work. We're also going to be looking at how our ears are connected to our brains and start to understand something more deep, have a deeper understanding of what it means to hear as a human. So all of this is presented now because it becomes really useful later once we start learning about computers and how they record sound, store sound, and then reproduce sound through headphones or speakers or whatever. What we'll find is that all of those processes, the recording, the storing, and the reproduction of sound, whether that be on a computer, a record player, whatever, really mirror both how sound works as like a physical phenomenon and how our ears and our entire hearing apparatus function. So all of this is really fundamental information for understanding computers and audio technology. So we start with sound itself and how we hear before we move into what computers do. So what I'll be going over today is the basics of sound, and really what I'm talking about is the physics of sound. What is it as a physical phenomenon? What are its properties? Then we'll be looking at the physiology of the ear. What are all the components, the individual components of the ear? How do they work? What do they do? Then we will talk about how the physics, the basics of sound, or our physics understanding of sound can help us understand what our ears are doing. And then, as I said, this all connects eventually to our brains, and that is where the process sort of becomes what we image as sound. So we're going to go through all of in detail. We're going to go through all of this. Be thinking, one way that you could keep track or follow along with the narrative of this lecture is, in one way, we are tracing a sound from, just take any sound. So you heard somebody drop a fork across the room and it hits the floor and plink, clink, 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 clink. Now, what the narrative of this lecture is doing is it's tracing that dropping of the fork through the air to our ears into our brain. So that's sort of the very general path that I'm following here. The sound, or at least the event that we perceive as sound, but the event traveling through the air, exciting our eardrum, going into our brains, and then we perceive it as sound. So that's one way to sort of follow along. So let's start with the basics of sound. What is it? What is sound? Some of you might be familiar with referring to sound as a sound wave. And sound is exactly that. Sound is sound pressure waves. We could also think of this in general. Well, I'm going to be talking about them as air pressure waves. But the reason we say sound pressure waves is because sound travels through all mediums, right? So if you've ever been in a swimming pool and then you hear people, from the surface while you're underwater, but you're still hearing them, sound is traveling through the water. We all have the experience of being annoyed maybe by somebody else who is your neighbor because you hear their music coming through the wall. So sound travels through all sorts of substances. I will be mostly talking about sound traveling through the air in all of these examples, but I'm just reminding us now that the reason I say sound pressure waves and not air pressure waves is because sound travels through all sorts of materials. So, sound pressure waves, what does that exactly mean? So when you think of a wave, let's really just kind of let's start with an ocean. So we're thinking of waves in an ocean. Of course, one thing that will come to mind is the ebb and flow of the ocean. So waves come onto the beach, they sort of crash onto the shore, then they recede back into the ocean, and then that repeats. And it's this ebb and flow, this wave coming up onto land and then going back in. Another way we could think of this, so, waves in the ocean, we could also think of ripples in a pond. So say you're looking at a pond, you're sitting by a pond. It's very calm, so you don't really notice the ebb and flow of the body of water. And you throw a pebble out into the middle of the pond, and you see those ripples emanate from where the pebble hit the surface of the water, and they emanate in all directions out towards the edge of the pond, towards the shore, and eventually they reach you. So in both of these cases, this will help you thinking about sound pressure waves when we're talking about sound, because two of these features are going to be really important. The ebb and the flow, or the sort of back and forth, and also the ripple effect, that waves travel from some point where something is excited. So you throw a pebble out into the middle of a pond, it creates these ripples from that point where the pebble hit the surface of the water. So when we're talking about sound pressure waves, they work the same way. Now, let's say I were to, well, I'll just clap my hands right now. When I clap my hands, or really any sort of like short percussive sound, will have this same sort of basic feature. What is happening? So what is it that my hands are doing that is producing sound? I'm moving my hands at a high rate, at a high speed, close together until they touch. Now, when they touch, in that moment, air is molecules. There's all sorts of molecules in the air. There's oxygen. There's carbon dioxide. There's dust. There's pollen. These days, we're really sensitive to the fact that there is human tissue in the air, so dead skin cells, mucus, all of that. That's why we're wearing masks. The air is molecules. When I clap, the air that is between my two hands, the moment that they touch at a fast enough speed, those air molecules get pushed together really fast. Now, air molecules we can think of as wanting to be at rest. And they come to at rest when they all have this sort of, to keep going with contemporary metaphors, you could think of air molecules as once all of the air molecules have the basically an equal amount of social distancing from one another, they're at rest. So they kind of like to just be in this web of equal distance from one another. So when I clap, I'm pushing all of the air molecules that are between my hands together really fast. Now, when they get pushed together, they want to go back to rest, and they jump back, to where they were with the same amount of energy, but that energy sort of pushes them close to air molecules that are next to them, right? So just like the pebble in the middle of the pond sends out these ripples, when I clap my hands together, it sends out ripples in the air. And what they are is like wiggles. They're wiggling the air back and forth. And when I push the air molecules that are between my hand out, when I sort of shoot them out from between my hands really fast, they get too close to the air molecules that are just outside of my hand. And so those molecules want to move away, and the next molecules want to move away, and the next molecules want to move away. And that pressure wave, if we were in the same room, would emanate from my hand and move out towards you. One pressure wave, okay? Now, that doesn't mean that what I'm doing is sending the same air molecules that between my hands out to your ears. The wave instead works like the wave at a baseball game. Okay? So if you're going to participate in the wave at the baseball game, you're not running around the baseball park. You wait in your seat, and you wait until the wave gets to you, and then you stand up, and then you sit back down. So the same exact thing is happening with air molecules when I clap. So as soon as I clap, I push this these air molecules that are in between my hands close together. They then push out towards the air molecules just outside of my hand, et cetera, et cetera, et cetera. All of these individual air molecules return to rest, but in order to do that, they are pushing their neighbors, and those neighbors are pushing their neighbors, and those neighbors are pushing their neighbors, all the way out to either to the microphone that's in front of my mouth right now, or out to some listener. So one clap would be sending out a pressure wave, just like a wave around a baseball park, just like one ripple in the middle of a pond. So it is a pattern of pushing air molecules together, pulling them apart, compressing them, rarefacting them. High pressure, low pressure. Okay? So, and to emphasize, they travel just like the ripples in a pond across space at a certain speed. So here, I'm building off of this last diagram where we're looking at the compression and the rarefaction of air molecules. The dots are air molecules. Here, you can see them push close together, then they pull apart, then they pull apart. This is a wave going through air. It's traveling through space. Here, we can see how you would get from this pattern of compression to rarefaction to one of the most important concepts in this class, which is understanding sound as a waveform. So here I think this is a nice demonstration of the relationship between the compression and rarefaction of the air and understanding it as a wave snaking above and below a x-axis or above and below a line that runs from left to right across your screen. So as you can see, you're traveling down we have three diagrams here. The top one is air molecules being represented as being pushed together and pulled apart, or what I'll be referring to it as wiggles. The air molecules are wiggling. They're rippling like the surface of a pond. So one way that, and then we can start to think of this as a general pattern of compression and rarefaction. In this second one, where maybe these individual lines in this middle diagram are averages, like average distance between air molecules. Then we can start to think of, you could represent this as a wave, as a sine wave. And this is the diagram that you see on the bottom here. So this is the waveform. When we start dealing with working with sound within a computer, we will be looking at waveforms all the time. And it's important for us to understand what we are seeing when we look at that waveform. What we are seeing is a visual representation of the compression and rarefaction of the air. Or another way to say that is we are seeing a visual representation of how the air is wiggling back and forth, how the air molecules are being pushed together and pulled apart. So when we're looking at this waveform, what we see is time and distance are moving from left to right. The average density or pressure of the air is the x-axis or the zero line. So that is air at its, where everyone is socially distanced the same amount. Air at rest, right? When air is pushed together, when it is compressed, it is going above the zero line. When air is pulled apart, it is going below the zero line. So when we're looking at waveforms, we are looking at these sine waves. Anything above the average density or pressure or the zero line that goes from left to right is going to be a positive value. Anything below is going to be a negative value. And the reason we think of that is it's whether air is being pushed together, which would be positive, or pulled apart, which is negative. Okay? So at the peak of the compression of air, or them being pushed together, the most that they get pushed together would be the crest of the wave, and the furthest that they get pulled apart would be the trough of the wave. Here's maybe a simpler way to break this down. When we are looking at the wave move from left to right, it's a representation of the air being pushed together or pulled pulled apart, or wiggling, the air wiggling at a certain rate in time. So one wiggle, which would be one full cycle. So let me get the mouse out here. So one full cycle would be here. We are pulling it down as far apart as the air molecules get. Then they get pushed as close together as they possibly can be, and then it comes back to the 0 point or them at rest. This is one full cycle. So one oscillation of rarefaction to compression. So when we talk about a cycle, that's what we're talking about. It crosses the 0 line. It has to cross the 0 line twice, essentially. So it enters into the negative, or enters into rarefaction, or enters into pulling apart of air molecules, and then it enters into pushing them together or into compressing them. So that is one full cycle. The faster that a wave cycles, the higher we perceive it is, the higher we perceive the sound, the higher, quote unquote, it sounds. The slower that the sound completes one cycle, or pushing the air molecules together and then pushing the air molecules together and then pulling them apart, the lower the sound will be perceived. Sound, these waves, so you can imagine if we were to compare this wave with one that was, if you're following my mouse, if we were to compare it with a wave that completed itself 2 cycles within the one cycle that we see here, it would sound higher, 1 octave higher to be exact. Sound is also happening in space. Like I said, when I clap, it takes a certain amount of time for that sound wave to travel from my hands through the air to either my ears or your ears or the microphone. So sound is also traveling in space. So we know that the wiggles are happening, higher wiggles are faster wiggles, and lower sounds are slower wiggles. So higher sounds are fast wiggles, low sounds are slow wiggles in the air, and they are traveling, whether it's fast or slow, at the same speed. Then we also know that these sound waves have a length in space. Now, we're going to dig into that later, and this is already, you might be like, wait, what? What? How can I be, when I look at this wave, how can I be looking at both time and space? Well, you're looking at space-time. Don't worry, this will become clearer when we dig into this, but when we look at a waveform and we go from left to right, we can see this as representing time, but we could also see this as representing space. Don't worry, all of that is going to become clear in a minute once we dig into the different characteristics of sound pressure waves. Then we're going to start to see, this kind of makes sense, how it could be both a representation of time. When we look at a waveform, whenever we're on a computer program looking at the visual representation of sound, we will always be looking at a waveform. It's going to represent each of these characteristics of sound. 1, amplitude. So that is really the same as loudness, as I'm going to try to convert these into like musical terms. So amplitude is like loudness. Frequency is how high or low the sound is. Velocity, obviously, is the speed of sound, which is always going to be the same depending on the temperature of the air. Phase is when we are looking at two sound pressure waves that are sounding at the same time, and how the compression and rarefaction, or the pushing together and pulling apart of two sounds, interrelate with one another. We'll also be looking at the harmonic content of sounds, and we'll be looking at envelope, or the shape of one single sound. Once we get through all of this, we'll be able to start making these connections, and I think that the connection between space and time will be clearer. All right, so who has seen this movie before? This is a classic. So this is, yes, it is the classic rock mockumentary Spinal Tap. If you've seen Spinal Tap, you'll know that this is probably one of the most famous jokes in the movie, and you can see here they've included with these with this storyboard, I guess, or just these like freeze frames, the dialogue between these two characters. So the guy on the right, or on the left, is the director of the movie, of this mockumentary about a rock band named Spinal Tap. And the guy on the right is Nigel. He is the lead guitarist in Spinal Tap. So, and the director's like, well, I'd like to do something on your gear. Let's look at your amplifiers. And so Nigel is explaining that, well, we've got the loudest amps of anyone. He's like, this one's very special because, as you can see, the numbers go to 11. And he's like, and I'm just kind of filling in some of what he says. He says, so yeah, when you just need that extra kick, just to take it up to 11. And then the director's confused, and he says, well, why don't you just make 10 louder and make the 10 the top number? And Nigel kind of like looks, and it doesn't really, and he's kind of confused. He's like, but these go to 11. So the reason I want to start with this is when we're talking about amplitude or loudness, we're always talking about scale. So, and what makes this joke so funny is that you can scale a range of loudness however you want to. I mean, you could scale, if the amps, if this amplifier can play the most quiet to the most loud, the numbers that you associate with that range, it's sort of arbitrary. You could go from 0 to 1, and then so instead of just seeing like 6 and 8 on this knob here, you would see 0.6, 0.8. You could scale it however you want. So I like starting here because when we're talking about amplitude or loudness, we're talking about how you scale the amount of air, or the amount of air compression that is happening. So the more that we can push air molecules together, the louder it's going to be, the more pressure there's going to be. So loudness is going to be about increasing air pressure. And so we can scale that in all sorts of ways. And what we're going to learn about is the main way that we scale it now, which is not from 1 to 10, it's not from 1 to 11. We are going to be talking about how we measure it in sound pressure level. So again, this amplifier that Nigel is talking about in the movie Spinal Tap, the way that any speaker works. So if you've ever seen a speaker, like a subwoofer doing some low bass or something, and the speaker is literally moving back and forth, right? The speaker itself is kind of going, I think we're probably all familiar with like seeing a subwoofer like shake back and forth. So what it's doing, it is pushing air molecules and pulling them apart, okay? That's how it's reproducing sound. It is creating wiggles in very specific tuned ways. So Nigel's amplifier does the same thing. It is a speaker cone that is designed to push out and pull back in, push out and pull back in. And the more air that it can push and pull, the louder it is going to be, or the more sound pressure it can create. So when we are talking about sound pressure and we want to scale sound pressure, we scale it into decibels, okay? So I'm sure that you all are familiar with this term, decibels. So decibels are the unit of measure for sound pressure level, or amplitude, or loudness, for loudness, let's say. And in order to calculate decibels, we need to use this equation. So beta equals 10 log 10 of intensity over 10 to the negative 12 watts per meter squared. What? Okay, so beta is the number of decibels, or dB. So whenever you see lowercase d, uppercase b, that means decibels. If you have a stereo at home, it probably says decibels on the little knob. I is for intensity, so this is the measurement that we are going to measure the sound intensity, or the amount of power per meter squared. So if we're looking at if we're talking about an amplifier, a guitar amplifier, the intensity is how much, how forcefully it's pushing the air out with that speaker cone. Okay, so power per area. So how much air is it moving? So if you've got a speaker cone that's 6 inches, if you got speaker cone that is 12 inches, if you got a massive speaker, like a huge subwoofer that, let's say it's like, I don't know, a diameter of 5 feet, like a huge one, right? It's pushing a larger area of air, right? The speaker cone is a diameter is 5 feet. It can push more air. So we have power per area. And that is, so the intensity, how much the air is being moved by whatever is being measured, is divided by the threshold of human hearing, which happens to be 10 to the negative 12. What? Okay, so I knew, like, when we're looking at this equation, you're like, I did not sign up for math. I signed it up for music. Don't worry. Like I said, I'm not going to be testing you on being able to do any of these equations. And but the reason I'm including them here is because they're fundamental to understanding music technology. So we will never be taking a sound intensity measurement and then trying to convert that into decibels. What we do need to understand is why the equation works the way it does, and why when we are making amplitude or volume changes within a computer program, why the changes are happening the way that they are. And we're going to be talking a lot about changing decibel levels within these audio programs. And changing decibels is not linear. What do I mean by that? Okay, so the range of human hearing is incredibly large. Incredibly large. So if we were to look at the range of human hearing from the quietest sound that we can perceive to a sound that is so loud it's just on the other side of pain or hearing damage, we have a hearing range of whatever that is, whatever the number is, 10 10 trillion units of intensity. The range of human hearing, when we're just talking about being able to perceive loudness or being able to perceive the wiggles, the lowest amount of intensity, which we see over here, which is like 0.0000000000001 intensity, if we could hear anything quieter than that, we would literally be able to hear changes in atmospheric pressure. So think about that for a second. If our hearing was any more sensitive as far as like being able to perceive quiet sounds, we would be able to hear changes in atmospheric pressure. So that's how sensitive our hearing is. And you could imagine how over the course of evolution, it would select for not being able to hear changes in atmospheric pressure. So if we were walking around just in daily life and we were able to just hear any random change in atmospheric pressure, whether that's brought on by a change in temperature or some other meteorological event, I mean, it would drive us crazy. So somewhere along the lines, evolution corrected for that and basically said, you don't need to hear that stuff. So, but here's the important thing here. The total range of intensity, or watts of power per square meter, is so incredibly great. So the question is, how do we scale this? How do we turn this, 10 trillion units into something that is manageable and that you could actually talk about? So, if you're thinking of Nigel's knob, his amplifier knob in Spinal Tap, it would make no sense to have 10 trillion little notches on there. So how do we scale 10 trillion units into something that is more understandable and comprehensible? That's why we use a logarithm. So what a logarithm does is it asks the question, what number would I raise my base to in order to get the number in the parentheses? Okay? So here, if we have a sound pressure level of 1 million, the log question then is, what number would I raise my base to? Log base 10. So log is always this is the base, in order to get the number in the parentheses. Here's the great thing about decibels. It's always log 10. So it's always base 10. And the thing about 10, as we know just from basic arithmetic, is that it's because everything is base 10 in our counting system, it's really easy to deal with any number with zeros, right? Because our counting system is base 10. So what number would I raise my base to, would I raise 10 to, in order to get to the number in the parentheses? So to kind of think about what the answer might be, how many times do I need to multiply 10 by itself to get to 1 million? 9 is the answer. And how do I know this? Because all I have to do is count the zeros. So log 10 of 1 million is 9. Now you're starting to see why this is useful, because I can use a logarithm to scale 1 million down to 9. So this means if I'm dealing with a range of 10 trillion, I can scale it to a much more reasonable range, something more like 100. Okay, so now we're back to our equation. Decibels equals 10 log 10 of intensity over the threshold of human hearing. So we're dividing by the threshold of human hearing because this is the absolute quietest sound that we can hear. We're putting the thing that is being measured, the intensity of the sound that we are hearing, above that. So, for instance, if if what we are trying to calculate here is let's say that what we end up with when we do this division, we end up with a sound intensity level of 1 million, or 10 to the 9th, 10 log 10 of 10 to the 9th, or 1 million, is 90 dBs. So a sound intensity level of 1 million is converted into 90 decibels. So we've scaled 1 million down to 90. This is why when we look at this representation of, this is the range of human hearing, you can see that it's bell-shaped, okay? This is why whenever we're talking about loudness, we're going to be talking about something, often people refer to it as exponential or logarithmic. And the reason is we're measuring in decibels. And the reason that we're measuring in decibels is because the range of human hearing is so extreme. So when I say that it's curved or exponential, that like here, we're seeing this exponential shape that is a product of decibels being measured through a logarithm. Okay, so in other words, 10 times 10 is 100, right? 100 times 10, right, is 1,000, right? 1,000 times 10. So each step as we're going up. So if we're stepping up through a log 10 system, the distance between each step increases. 10 times 10 is 100. So we go from 1 to 100. 100 times 10 is 1,000. So the next step, the next notch on the knob, it's goes from 10 to 100 to 1,000. You get the pattern. So each step is increasing, and that's why we see this sort of bell shape as we're going up through the logarithm that represents the range of human hearing. The higher the steps are, the more steps in sound pressure level are being represented. So here we can see the whole range of human hearing mapped onto decibel level. So this is the very bottom. This is very quiet things. Here we've got rustle of leaves, very faint. As we're going, and that's around 10 decibels. As we're increasing up this range, right, we're getting into more musical sounds. Full symphony orchestra playing very loud, a hi-hat strike, a live rock band is just below a live rock band is actually like above the threshold of pain. This is why we should all be wearing earplugs when we go to a rock show. So the threshold of pain this is where we're starting to be like, oh, this is loud. Maybe your ears ring afterwards. The closer we get to intolerable, the closer we are getting to actually potentially having permanent damage. What this is all measuring, what these decibels are all measuring, are the amount of, or just how much air pressure is being produced by the sound, okay? So a decibel reading is reading how much air pressure is being produced. And this is exactly why there is a correlation between physical pain and damage and decibel levels, because the more air pressure is, the more it's going to affect our bodies. Okay, so that takes us through amplitude or loudness. And we're understanding amplitude or loudness in a couple ways now. The amount of air pressure, or how much the air is being compressed together and pulled apart. We're also thinking of it as decibels. So we're scaling that air pressure from a huge range into something more manageable. So we're scaling it down from 10 trillion into something more like 140 notches. Or less, more like 120 notches. So it is something that we're scaling into decibels. So we're measuring amplitude or loudness in decibels. We are also understanding it as how much the air is being displaced from rest, how far the air molecules are wiggling closer together and pull further apart. How much the pressure, how much pressure there is. And pressure, it correlates with how close air molecules are being forced next to one another. So that is loudness, or dynamics in musical terminology. Now let's move to frequency, or how high or low an individual sound is, or to speak in musical terminology, pitch. So here we have, of course, Albert Einstein. I like throwing. Let's go back. I like throwing this in here because we're just talking about the space-time continuum, which comes from Albert Einstein's theory of relativity, and it's cool to realize that Albert Einstein was also a musician, and that playing the violin and going to concerts was a really important aspect of his life as a creative person. So here he is playing a specific frequency or two that he's reading off of a sheet of music, Albert Einstein. So what is frequency or pitch? So when we're talking about it in here, and this is going to be really useful when we start messing around with sound and music in these programs, is frequency or pitch is measured in hertz. Okay? Now, one way to think about this. So hertz, or the number of compression to rarefaction cycles per second. So remember, we're talking about air being pushed together, pulled apart, and coming back to rest. That's one cycle. Or the number of times per second a sound wave completes itself or cycles through. So frequency here, like how frequently does one cycle of compression to rarefaction, or one time through the sound wave, crossing over into the positive values, crossing over into the negative values, and back to rest. How frequently does that happen per second? How many times do we get a wave that completes itself per second? So one wiggle. How many of those happen per second? So the frequency range of the human hearing is roughly from 20 hertz, or 20 wiggles per second, 20 full wiggles per second, all the way up to 22,000 wiggles per second. So in other words, and I mentioned this before, the slower the frequency, the fewer wiggles per second, the lower we perceive the sound. The faster the frequency, or the more wiggles per second, the higher we perceive the sound. So if we're looking at this representation of a wave here, and again, to go back to this concept of scaling and how we were representing it with numbers, and let's say that this line is, as it says here, is measuring time. Okay? So let's just say that at this cycle start point, let's say this is 0 seconds. Okay? And let's say this cycle endpoint is 0.05 seconds. So if we were to compare that, one wavelength taking 0.05 seconds, and we were to compare that with one wavelength, let's say, taking 0.02 seconds. So now we're imagining this same exact representation, but instead of going from 0 to 0.05, it goes to 0.02. how would the resulting sound be different? So, if you said that the wavelength that is 0.05 seconds long would be lower, would sound lower than the wavelength that is 0.02 seconds long, you are correct. That the quicker it is, the shorter amount of time that a wave takes to complete itself, the higher the resulting sound. So we have, like I was just mentioning, we have a hearing range of from 20 hertz or 20 wiggles per second to 22,000 wiggles per second. So here we have this really fascinating graph that's comparing our range, our frequency range. Again, we're not talking about loudness, right? We are just talking about frequency now. These frequencies, of course, could be played at any number of levels of loudness. So we're just talking about how, in other words, we're talking about how fast the wave is completing itself or oscillating. We are not talking about the amplitude. We're not talking about how far the wave goes up to reach its crest or how low it goes to reach its trough. Right now, all we're talking about is how fast it's doing it. So a very quiet wave would be that at this same frequency would be something like this, right? It's crossing the 0 point at the same time. It's just not pushing the air as much. A louder one would look something like this, right? So it's still crossing at the same time. It still has the same speed. It just has more power. It's pushing the air more. So if we're to come back, here we are with this interesting graph that's comparing all of these different species and their range of hearing in regards to frequency, not to amplitude or loudness. So here we see humans are this sort of fuchsia color. Here's our range from about 20 hertz all the way up to, and again, you'll probably notice this is scaled logarithmically as well, all the way up to 22,000 hertz, okay? But let's, just kind of like looking at all these different species. I mean, check out that ferret. That ferret can hear really low. Here's the ferret right here. Can hear really low sounds and then can hear high sounds that we cannot hear. Dog can hear, doesn't hear some of these low sounds that we hear, but definitely hears some higher sounds. What are some other impressive ones? Of course, a little brown bat, half of it has this very small range of hearing, but really is just only hearing those high sounds because it's using its own, it's sonar. It's using its high squeaks to perceive space. And this porpoise has this really amazing range of hearing, can hear really high sounds. Again, a porpoise using sound, its calls in the water to like radar to perceive space. So animals that are using their own sound to perceive space have this can hear incredibly high sounds. So, our range stops at 22,000 hertz. The range of these animals that are using echolocation reaches up to 100,000 hertz. I mean, that's crazy high sounds. Let's see who's kind of the saddest. Yeah, some of these like birds, which is kind of interesting that like a canary or a cockatiel, we hear higher sounds than they do. We also hear lower sounds than they do. They're kind of stuck in the middle ground. Okay, so I like looking at this just as a reminder that what we hear as humans is just part of reality. Think about that for a second. There's this whole range of reality when we're talking about sound that we never even experience. And that range of reality is like most of what a bat experiences, for instance. Same on the bottom end, So what we hear is just a small bit of reality. If we could hear higher, we would be able to, for instance, or when I say higher, I'm talking about frequency. We would be able to hear radio frequencies. All of those are outside of the range of human hearing, and they're very fast. Okay, so we're moving from one type of speed to another type of speed. We're moving from the rate of wiggles, how fast the air is wiggling back and forth, to how fast that wave travels. All right? So we're talking about now the speed of sound, not the speed of the wiggles. Right? The wiggles is how fast the air is pushing back together, and then you can think of the wiggles the frequency as the speed of an individual air molecule going from rest to close to its neighbor to far away from its neighbor back to rest. The speed of sound now is how fast that energy transfers from that first air molecule to its neighbor, to the next neighbor, to the next neighbor, to the next neighbor. Now we're just talking about the speed of transfer, not the speed of the wiggle itself, or the rate of the wiggle, I should say. So maybe we should stick with rate for frequency. Now we're talking about speed as how fast sound travels. So here we're looking at a aircraft as it is breaking the sound barrier. And it creates this cloud behind it. So the aircraft is now moving faster than the speed of sound. Now, the reason that it creates a cloud behind it, we're not seeing that's not what we see, is actually a collection of condensation that is a result of breaking the sound barrier. But the cloud is not. We're not actually seeing the sound. We're seeing like this a atmospheric result. But this is what happens when airplanes break the sound barrier. They create this like cloud of condensation behind them. So, and what that results in is a sonic boom. Okay. So when we're talking about the speed of sound, a good way to understand this is to talk about the phenomenon of the sonic boom. So here we see Indiana Jones, and he is, of course, he's about to crack a bullwhip. Now imagine that sound in your head, the snap or the crack of a whip. Whoosh, right? You hear the whoosh and then the snap at the end. Now, at the end, when the whip cracks at the end, when it snaps, that loud crack, it turns out that is not the sound of leather, of the end of the whip sort of smacking together like you're clapping your hands. The whip is not smacking. What the whip does at the very end of it is it goes faster than the speed of sound. So whenever you crack a whip, you're creating a mini sonic boom. Isn't that cool? Think about that for a second. So yeah, the crack of a whip, or even when you crack a towel, it is creating a mini sonic boom. And what does that mean? The very end of the whip, the very end of the towel, whatever it is that you're cracking, that very end is traveling so fast that it crosses the sound barrier. Okay? So sound travels through the air. If the air is 68 degrees Fahrenheit, sound is going to travel at approximately 1,130 feet per second. As the temperature of the air increases, the speed of sound also increases. Now, this kind of makes sense, right? Because if we know that sound is air molecules being pushed together and pulled further apart, and we kind of know that the hotter a material, say like you're cooking or whatever, like as you increase heat in any sort of matter, it sort of loosens up. And when you freeze something, like you freeze water into ice, it becomes more rigid. So same phenomenon when we're talking about sound traveling through the air. When the air is colder, the molecules are more rigid. So sound is going to travel a little bit slower. As we increase the temperature of the air, the sound molecules are going to be looser in a way, more fluid. And that is going to result in a faster speed of sound. But in general, for our purposes, we're really thinking of sound as traveling around 1,130 feet per second. So now let's take this back to the sonic boom. So we know that sound is traveling at a particular speed, okay? And we know that sound operates like, we know that sound is waves. It is consistent, compressing and rarefacting the amount of space between air molecules, or increasing air pressure and decreasing it at a certain rate. In other words, let's go back to our pond metaphor. So the waves act like the ripples in the pond. You threw out a pebble into the middle of a pond, and it creates these ripples that emanate towards you at the shore. So let's imagine a plane flying above that is sending out ripples, right? Ripples of sound. Of course, the plane is traveling, so if we're imagining these ripples going out all at the same, in all directions at the same speed, we have a plane that's traveling. So if the plane is, let's say the plane is traveling, let's say you're following my cursor across the screen, here is the plane traveling from left to right. So, and there are ripples going out at the same speed in all directions. So the ripples that are in front of the plane are going to be closer together than the ripples behind it, because the sounding source, the source of the sound, is also traveling at a speed. And the ripples that go behind it are going to be further apart than the ripples in front of it. This is what when we're talking about the Doppler effect, this is exactly the phenomenon. So think about every time that you've heard an ice cream truck and it drives and it's playing that ice cream truck song, and the truck is coming towards you, right? It's getting closer, it's getting closer, it's getting closer. Okay, now it passes you, and then it goes away, right? And as that happens, you hear the sound of the music. It seems as if as it passes you, that the sound of the music gets lower. And that's because as the source of sound is coming towards you, it's pushing all of those sounds a little bit closer together, right? And as it's going away, it's pulling just a little bit further apart. So that affects the wavelength of the sound. It's the Doppler effect. Or think of any time a car just drives by, right? That is the Doppler effect. And so what you hear is the sound of the engine emanating from the car in a series of waves, of wiggles, as the car is approaching you, those wiggles are pushed together just a little bit, right? Because each wiggle has a little bit of extra speed added to it because of the engine of the car. So it goes, and as it passes you, now they're being pulled apart just a little bit. Okay, so that's the Doppler effect. What happens with the sonic boom is the speed of the plane becomes more than 1,130 feet per second. So all of those waves that the engine is creating get put on top of one another, and it creates a very loud sound. So if we're going to think, so we're thinking, and this is when you crack a whip or when you're in a plane. So to think, I'm just coming back here to just imagine. So here is the sound of the engine, right? Moving out in space. This is the wave. Once we cross the threshold, the speed of sound, we get multiple copies. It's kind of crazy that it works this way, of this wave on top of itself. And so what happens when you multiply when you add 1 to 1, you get 2. So you get more amplitude, more loudness. You're adding one exact wave on top of itself. That is the sonic boom. That is the sound of an airplane crossing it. It is also the sound of a whip cracking. What it is producing is it's adding one single sound on top of itself, which is kind of crazy to think about. Okay, so let's move on into thinking a little bit more about the speed of sound and what that would have to do with music technology. So let's say we have a wavelength of 110 hertz, which is a natural. It's probably right about the range of where I'm speaking right now. So this is about 110 hertz. Yeah. So we have that sound, which is a waveform of 110 hertz. Let's say that it's in a 68 degree Fahrenheit room. Can you figure out how much space, or in other words, if I were singing that note for you, and that waveform, or my vocal cords are wiggling the air back and forth and compressing it and rarefracting it, pushing air molecules together, pulling them apart at a certain rate. And that rate is 110 times per second. 110 times per second, right? And we know that rate, that sound, is now traveling from me to this microphone, and if you were in this room with me, to you, at a rate of 1,130 feet per second. Wiggles per second. Feet per second, okay? Can you figure out how much space, how much distance that sound would travel before it created one cycle, or one pushing air together and pulling it apart and coming back to rest? I'll give you a second to see if you can think this through. All right, we're able to figure it out. Well, I will actually rather than giving you the answer now, I will let's see if people can answer this and bring their answer to the next time we meet. So here's the question: can you figure out the wavelength of a 110 hertz waveform in a 68-degree room? We will work through this equation next time. Okay, so that really kind of concludes the velocity or the speed of sound. So we've looked at three things already. We have looked at amplitude or loudness. We have looked at frequency or pitch. And we've looked at the speed of sound. Now, and all of that was just dealing with one sound. Of course, when we're, or one one periodic disturbance in air, or one periodic waveform. Of course, when we're dealing with music, we're almost always dealing with more than one sound, okay? So this is, when we're talking about this in terms of music technology, the term we're going to use is phase. Okay, so here in front of you, you see this animation, and on top, you have two thinner waveforms, and on bottom, you have a thicker one. Okay? So, the way to sort of to think about this representation here, what this is it's the on the bottom, this is going to be the heard result, okay? So that's going to be what you hear when you combine these two other waveforms. These two other waveforms are happening, they are two different frequencies. There are two different rates of wiggle, okay? So if we're imagining this screen as time is going by at, really, it would be the rate of 1, 2, 3 cycles through this top wave, and that's why we don't see it moving, because you can imagine the camera is traveling at the speed of this, of the rate of this top wave, okay? This bottom wave is faster, right? So so that means this bottom wave is going to be a frequency that we are going to hear as higher. So you could think of this as two different pitches playing at the same time. Now, we know that waves represent compression and rarefaction, or air being pushed towards you and pulled away from you. And we also have talked about waves as crossing a 0 point. So numbers that, measurements of amplitude that are above the 0 line, or the x-axis that the wave is crossing over. Values of amplitude that are above that are positive, and values that are below are negative. So if we were to play these two patterns of pushing air apart and pulling it, pushing air towards you and pulling it back, if we have two patterns of pushing and pulling happening at the same time, sometimes the push cancels out the pull, okay? So if you've got two sounds that are happening simultaneously, they're acting on the same air molecules, right? They are waves happening within the same room, acting upon the same material, which is the air. So when one wave is compressing, if the other wave is rarefacting, the result is they're going to cancel each other out in some sort of pattern. So that is the result that we see on the bottom, right? So what we see, this kind of like coming back, this sort of like snaking that's happening on the bottom, is we have these two sounds, And sometimes they reinforce one another, and sometimes they cancel each other out. And so we hear this phasing or beating effect. So we all are familiar with this. Like if you were to play two notes on the piano that are low and that are very close together, you would hear that whoa, 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 whoa. So that wah, 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 wah. That wah, 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 wah is we are listening to a pattern of cancellation and amplification between two notes or two different frequencies or two different speeds of wiggle between those two piano notes. And so this representation at the bottom is going to be the overall amplitude effect of that beating, that phase, okay? So whenever we're thinking about this, be thinking about how multiple sounds are creating new patterns. So one sound is going to have a frequency, and that's one pattern that you are letting out into the room. So if you're singing, you're like, ah, that you're letting out a pattern, a frequency, a rate of wiggle in the air out into the room. That wiggle is going to interact with the other wiggles and create much more complex waveforms than these very simple sine waves. So when we start looking at waveforms in computers, they're almost never going to be as smooth and simple as this because there's all sorts of phase cancellation that's happening. That's the result of other sounds in the room. It's the result of the sound bouncing off the wall, reverberation. All of these things create these much more complex patterns of compression and rarefaction or complex wiggles. So once we start we're never going to really see this sort of pure sine wave unless we're producing this pure sine wave with a computer or some sort of technology. Acoustic sound, most of the sounds that you're going to be dealing with are going to be much more complex because there's going to be some sort of like interference, and that's really what creates the richness in sound that we are used to. So now we're thinking about how two sounds can reinforce one another or cancel the other out. This relates back to what I was just talking about with the sonic boom. If we have the same sound and we put it on top of itself, it's going to be twice as loud, right? So when we cross the threshold of sound, the speed of sound, when we cross the sound barrier, our sound is amplifying itself. When, let's say we go back to the speed of sound and the question that I asked about, can you figure out how much distance, like in physical space, how many feet, say, it takes, feet. It takes a 110 hertz sound to go from compression to rarefaction back to zero. This equation becomes super important because just like the sonic boom makes a loud sound because it takes one sound wave and puts it on top of itself because it's moving faster than the speed of sound. Similarly, let's say I am singing my 110 hertz note, and let's say you are recording me at, you have two microphones. You're recording me in this room, right? And you have a microphone that is the distance from me that is the same. It's the same as the wavelength of my note. Or in other words, if you figured out how long it takes a 110 hertz wave to complete itself in physical space, let's say, so it takes the distance of one time through the wave. So one from one crest to another crest, okay? Now, let's say you put a second microphone in the room, right? So here I am starting my note, or let's say I'm starting my note from this zero point here, right? And you put a microphone right here. So right where the cycle completes itself. Let's say you put a second microphone, and you put that right here. So the first microphone you put where my note is crossing from negative territory into positive territory, or from air being pulled apart to air being pushed together. And you put the second mic where my note is crossing from positive territory into negative territory, or it's going from pushing air molecules together to pulling them apart. But you're right. If you put those two mics at those 2 points, the result would be that my sound would cancel itself out. You would end up with phase cancellation. So that's why knowing knowing the connection between wavelength in space and wavelength in time is super important. Imagine this becomes super important for recording engineers when they're setting up microphones around a drum kit, because you always are going to need multiple mics on a drum kit. And if you end up putting 2 mics in there and one mic is a full wavelength away from the snare and the other is a wavelength and a half away from the snare, the snare seems like it's disappearing. So this is something that it's very practical knowledge is what I'm saying, understanding phase. Another aspect of sound that, so again, we're traveling out of, we're traveling away from the most simple sound, like understanding sound in, like, I guess a laboratory setting, which is a sound wave, and now we're coming out into the complexities of acoustic sound. So the other thing that happens with sound and resonance is that, like I said, a perfect sine tone, which again is going to be just one very simple oscillation of air being pushed together and back and pushed together and pulled apart at a consistent speed, at a consistent rate. A computer can produce that very perfect, smooth transition. But any acoustic sound is never going to do that. Is never going to have that very simple, it's just that frequency of back and forth. There's always going to be some weird, I guess you could say, interference between different patterns. And acoustically, in any sort of resonant body, and when I say a resonant body, I'm just talking about a musical instrument, a guitar, a flute, a piano, a drum, your voice. What happens is you end up with these different patterns different patterns of different wave patterns that all stack on top of one another. And what this is the harmonic series. If I were to play a guitar string, say, if we're looking at each of these are just different examples. Let's say we're looking at one string. So imagine one string crossing through this top figure. And the red and blue lines are representations of how far that guitar string, I pluck it, right? So I pull it out and I let it go. And the string itself is now it's compressing the air and rarefacting the air. The string is going back and forth, back and forth, back and forth, wiggling, wiggling, wiggling. And if this figure, this drawing up here, is a representation of the string pushing out towards us and pulling away from us, wiggling, compressing, and rarefacting the air, right? But the thing is, when I pluck that string, I let energy into it, and that energy travels down the string in both directions. So if I pluck the string on a guitar over the soundboard, imagine I just, like in a very traditional way, I plucked it over where that sound hole is on a guitar. The energy is going in both directions down the string. And then the energy of that pluck is traveling back and forth, back and forth, back and forth across the string. And the result is you end up with vibratory patterns that divide the string into whole numbers. So it divides the string, so you're going to have the string, the whole string is going back and forth, but once that energy is transferring back and forth between the bridge to the nut, or one end of the string to the other end of the string, it creates this sort of pattern. So it divides the string in half, it divides it into 3, divides it into 4, divides it into 5, divides it into 6, divides it into 7, and so on. And those divisions end up also being multiplications of the frequency. So if the string is 110 hertz, dividing the string in half is 210 hertz, or 220 hertz. Dividing the string into thirds is going to be 110 times 3, which is 330, 440, 550, et cetera, et cetera, et cetera. And that creates the harmonic content that you're going to hear in in any string. And let me see if I can. I'm going to grab my guitar and demonstrate this. So I have a guitar, and I'm just going to play the low note. So that's the low note. Let's see if I can, if I just touch the string halfway through, I'm not pushing down on the fret. I'm just barely touching the string. Here it is. This is like a third of the way on the string. A fourth. A fifth. A sixth. Seventh. That one's hard to get. There we go. So I'm just touching the string, and I'm able to isolate those divisions. Now, when I play this string again, oftentimes when you listen to a string slowly lose its energy, when you just listen to it sort of die out, you can start to hear some of these higher sounds, some of what we call harmonics, emerge. So think back to some time that you've heard, it's especially effective on acoustic piano, like a low note hit loud, and then it just is let to resonate. And so a lot of times it'll be like, boom. Like you might hear those higher notes sort of come out as the energy of the string is dissipating, and you're able to hear some of these other vibrations. The timbre of any instrument is produced by, or what we hear as the tone color. That's another word for timbre. Like the sound of that particular instrument is how it's resonating, and the resonating, or how it's vibrating. And the way that a particular instrument vibrates will emphasize these different vibratory patterns happening within the note that's being resonated, or the lowest wiggle. So again, the best way to think about this is a string. So the length of the string here is always the same in all of these different. It's like a jump rope, right? So you're playing jump rope, and then you go to double Dutch, you go to triple Dutch, right? The same thing is happening within any plucked string. And the result are different frequencies. So when you hear a string vibrating, it is just one note. Let's say it's a low E, but the different frequencies you're hearing are a very loud low E, and then a quieter E an octave above that, and then an even quieter B above that E, and then another E, and then a G sharp, et cetera, et cetera. And this is the harmonic content of any acoustic sound. So in the laboratory reality of sine waves, we can hear just one frequency. But whenever we're hearing an acoustic sound, we are hearing many frequencies at once, is the main point here. And don't worry, we're going to come back to harmonics a bunch later when we're talking about resonance and filters. But for now, this is to emphasize that acoustic sound is much more complex than just one frequency at a time. Okay, we've covered a bunch. We've covered amplitude or loudness, or how much sound pressure is being created, or how closely together the air molecules are being compressed. We've talked about frequency or pitch, or the rate at which the air molecules are being wiggled or pushed together and pulled apart. We've talked about the speed of sound as consistent with based on temperature. So low sounds travel at the same speed that high sounds travel. We've talked about how a moving sound source, whether that be an ice cream truck or a plane or a person, that motion is going to affect how we hear the sound if we are standing in place, because sound travels at a particular speed. We've talked about multiple sounds happening simultaneously. And so if you have multiple sounds happening simultaneously and they are different rates of compression and rarefaction, or different rates of pushing together and pulling apart, then sometimes those pushing and pulling will cancel each other out. So we've talked about multiple sounds happening at the same time. We just went over how single sounds are also multiple sounds. In other words, a string, a pipe, a flute operates in the same sort of way that any sort of resonant or any sort of sounding body, whether it be a drum head, a guitar string, a flute or a pipe, or even your vocal cords and your body, are going to create new patterns because the sound is bouncing back and forth along the string, along the pipe, from the drum, the rim of the drum. So you can think of the drum almost like a pond. You're striking it, the waves are going across the head, the drum head, they reach the rim, then they bounce back in. Same thing with when you're singing or speaking. So you're pushing air through your vocal cords. They are sending that energy up through your throat into your mouth. All of that air is bouncing back and forth within your mouth, within your throat, creating new patterns because the air is bouncing back and forth. So you have more than just that lowest sound. You're going to create these other sort of, these other patterns, harmonics. So we've talked about how sounds are always, so not only do sounds interfere with each other if they're multiple sources, single sounds create all sorts of intricate and complex interference patterns within themselves. This last topic is now talking about envelope or the shape of a single sound, okay? Any sound is going to have a general shape, and this is going to be, we're going to come back to this so many times over the course of the semester. this is a way that we can describe any sound, and whether it be acoustic sounds or electronic sounds, etc. And we're talking about time and amplitude here. And again, this is thinking about a sound as in I plucked a guitar string or I clapped my hands or whatever. And we're thinking now, and whereas before when we were talking about amplitude, we're thinking about such a small amount of time because we're thinking about frequency, which is like whatever. Even a low sound is, the lowest sound that we can hear is 20 times per second, which is very fast. But now we're talking about time on a on a different scale, not on the sort of microscopic scale of talking about frequency. Now we're really talking about being able to describe individual sounds. So a guitar sound. So I'm gonna do two sounds, and we can kind of compare them and describe them as far as their envelope in two different ways. Or sorry, two different sounds are gonna have two different envelopes. Okay, so we've got. Haven't tuned this guitar, but whatever. So that's the first sound. Here's the second sound. Okay, so same chord. Obviously, I performed it in very different ways. The first performance, I let it resonate, or I let it sing out for a longer amount of time. The second one, I cut it off really short. So any sound is going to have these features, these elements. There's the attack, there's the decay, there's the sustain, and there is the release. So the attack is the initial onset of the sound. It is the very moment that I put energy into those strings. And it's when we're talking about those two sounds that I made, it's going to be the highest amount of the most amount of amplitude, or the most amount of displacing the air. Then the strings, at least in the first time that I played it, the strings then kind of come to a sort of stable mode of behavior where the energy is sort of moving back and forth along the string, and then that energy starts to dissipate, because every time that energy that I've released into the strings goes back and forth along the string, it loses energy, right? It dissipates because it has to move the string, it has to move the air around it. Each time it does that, it loses a little bit of energy, and this is what we would call the release. Now, guitars, unless you have an EBow, are generally going to have this kind of a shape, where you're going to have an attack that reaches up to the loudest point in the shape of the sound, and then it's going to sort of come to a state of periodic resonating, or just the strings just kind of going, and then it kind of dies out. But for instance, if you play a brass instrument, you know that yes, you could make an envelope that's like this, like burr, 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 right? But you can also make a very subtle, smooth attack, so it almost like it kind of fades in. It's like, so the envelope, when we are using these different terms for the different elements of the envelope, that this does not mean that the attack can be very slow. The attack can really just kind of move up to a sustain of the sound, and then it can release. The release can be very long. It can be very quick. All of these ways are ways to describe the shape of any given sound in time, and what we call that is the envelope. So the envelope of sound. Okay, so that has taken us through the first half of this week's lecture. we have covered a whole bunch of stuff. We have covered the waveform. We have looked at amplitude. We have looked at frequency. We have looked at velocity of sound. We've looked at phasing and harmonics. We've also looked at envelope. That's a lot. I think that is enough for now. We will continue with the physiology of the ear and how we perceive all of this physical stuff next time. So, have a nice day, and we will see you next time with the physiology of the ear.